come back and take it out. We don't want it. No.
Okay, so I'm very pleased to introduce Bryson Brown. He's going to be talking about paraconsistency and pluralism in science, and is well known for talking about paraconsistent strategies in scientific reasoning. So please.
So I wanted to thank Maria, Luis, for organizing and getting this thing running, and also for the lunch we enjoyed this afternoon, which has left me comfortable and sleepy. And I'll try to be on my toes despite that and get through this story. I think that scientific inquiry is local. We tend to focus on particular questions we have about particular objects, particular events, particular processes, kinds of processes. So it has a kind of narrow focus. So particle physics, parasitology, glaciology, vertebrate paleontology, all of these sort of seem to have, as some people say, their domains. And we can divide these in turn. So you have people today who are very, very interested in the half-life of the neutron because there are a couple of pretty good experiments that, within the levels of precision expected, disagree. So there's something mysterious about, at this point, the half-life of the neutron. And we also see sometimes separate fields conflicting. So this has been mentioned already, I think today, the 19th century dispute between historical geology and Kelvin's geophysics. This is an interesting issue because you're asking questions about the standing of the physics, which is questionable, and you're asking questions about the degree to which historical geologists at the time really had a strong case for the age of the Earth. Darwin famously made a calculation in the first edition of Origin that was withdrawn somewhat later. To his embarrassment, he said he burned his fingers on that one, even though, in fact, he was more or less right, as we see it today. I think that by allowing partial independence to different scientific inquiries or projects, pluralism, sensible project. It focuses on science as we find it, not as we imagine it might be, not as this ideal finished project. It's nice perhaps to have some idea of what an ideal finished project of science might look like, but that's pretty speculative today, and if we really want to talk seriously about science, we have to start with what we have. So I think that's a nice, modest approach to thinking about science. Start with the thing that's before us. But it does raise these kinds of logical puzzles about how we reason in science. When we have incompatible principles used at different points in the scientific story about the Earth, or atoms, or satellites orbiting the Earth, as we heard earlier, you're not going to close all of the story you're telling under classical consequence. It doesn't mean necessarily that you're committed in some strong sense to paraconsistency, to the truth of contradictions, or even to the truth of contraries. But you're not going to put all that together and close it under the classical turnstile. So we need some kind of paraconsistent reasoning to deal with that. And that brings me to Belknap's question, which he asked me, I think, in Montreal at an SEP conference in the 90s. What logic is a scientist using? And the reason the question is hard, of course, is because scientists rarely say, I'm using classical logic here. They argue in English or some other language, and they'll do the math in, to some extent, proper formal style, but physicists are notorious for being pretty free and loose with how they do the math as well. At any rate, we get this question in the philosophy of logic here. Which do we get first? Do we get logic or the less systematic actual practice of reasoning in science, and before that in natural languages? And I think the answer is pretty clear, really. We start off with the very informal practice of reasoning. And logical theories, some of them incompatible apparently with each other in terms of how they treat various kinds of consequences, emerge as at least partly efforts to give a systematic account of that practice of reasoning. So I would treat paraconsistent logics, while some people think of them as always having been there in the background, really, right, present, I would say they're proposals for systematizing a practice which is already clearly, to some degree at any rate, inconsistency tolerant. So what does symbolic logic give us? It gives us this lovely, rigorous way of expressing what commitment to a theory involves. Commitment to a theory means you're committed to the closure of that theory under whatever consonance relation you're positing or accepting. And that's really nice, because you get logical closure, you get infinite value, an infinite collection of sentences out of a finite input, and you get it in a nicely determinate way. And this tells us how, once you've adopted this view, how unstated commitments follow or arise from the things that you actually have said. And it does so, again, very systematically, so it's not just a matter that you and I could differ on. We can resolve that difference. I can give you the proof or show you in the semantics that this actually goes through. But real science is always at risk of encountering inconsistency, and therefore, according to the usual family of logics that people use, just classical logic or intuitions for that matter, or a number of others, you're risking trivialization then. If science comes across an inconsistency, you find that's in your theory, the theory just collapses, no matter how much good work you've done with it up to that point. Now everything follows and it's just nonsense. And we get, nevertheless, despite that threat, we get in the history quite a number of interesting examples where people do apparently reason in a more limited way, in a non-trivial way, from inconsistent premises. Calculus, we've seen, Bohr's hydrogen atom, theory of the hydrogen atom has been mentioned a few times, the Dirac delta function also. And beyond these examples, of course, there are familiar philosophical puzzles that create the same kinds of tensions around notions that we might think of as more fundamental or more, at least having been around longer, like the notion of truth in the liar context, or Zeno's paradoxes, just the idea of motion, or the idea in the case of the paradox of measure, how you can divide a certain unit of space up into an infinite number of points and get all of those points have zero size, and how can they compose a non-zero sized interval. These things seem to be extremely troubling. And what we want to have in at least our hip pocket, if we encounter these things, and they've been around for a long time, is a way to systematically reason in that context. And from my perspective, it doesn't matter whether we take that context to be one in which, yes, we're committed to the truth of these inconsistent theories. It's just a matter of wanting to reason with them for the mieux, perhaps. So we've got to get out of this situation in which we only have a logic which tells us we're done when we run into inconsistency. We want to have some logical tools to work with that give us a closure operation that doesn't just tell us you've got nothing whatsoever of any use because you're committed to every sentence. You can't make any distinctions anymore. A practical response here is to isolate the context in which these inconsistent commitments arise. It might not always be applicable, but in some contexts it seems to be a useful response. And you can get out of that, for instance, the weakly aggregative logics that Scott and Jennings proposed. Or you get A, you get not A, but you don't get the conjunction. That's still trivial because you don't get full aggregation. And sometimes, though, it seems important arguments cross boundaries that we might want to impose if we're going to try in some way or other to systematically keep these things separate. And so isolation doesn't always seem to be the right response. Especially if you want to reason through and rely on one in one context of the course of your argument and then draw on the other in the other part of your argument. And maybe you can do that systematically in a way that's non-trivial. And that's the thought that inspired Chunk and Permeate. So what we have here, I think, is nothing like a logic. It's an inference strategy. It's a reasoning strategy. Some people have broader, sort of fuzzier boundaries for where logic stops and other things start. But the idea is we add to the separate commitments a permeation relation, which allows certain sentences to go from one context to another. The two contexts may be inconsistent, or there may be more than two in general. The two contexts may be inconsistent, but so long as the material that gets passed along is consistent with the cell that it's passed into, or the chunk that it's passed into, then of course we don't get trivialization in any of the chunks. So it gives us models of reasoning with inconsistent premises that avoid contradictions and retain inferential links between those inconsistent commitments. So here, specified kinds of conclusions that are inferred from some premises, so this is just more of a detail, permeate into further reasonings relying on perhaps contrary premises. And in the end, in what's called the target chunk, we obtain conclusions that draw potentially on all the available premises, but in this constrained, non-trivial way. Now, I can give you the formal definition of CNP structures. I'm sure some of you are already familiar. It's a tuple, if you like, a three-tuple. And P is a consistent covering of gamma. So we divide some set of commitments, which is inconsistent, up into some number of cells or chunks. Rho is a permeation relation, which tells us what sentences and what chunks can be transmitted into other chunks when they're derived. And then we have a designated chunk, which is where we're going to draw conclusions. So we can make use in the reasoning of inconsistent premises, but we never combine them in such a way to trivialize at least the target chunk. I don't mind if another chunk trivializes. You can always actually rewrite this structure then so that you don't have trivializing chunks. So they arise from a sequence, the conclusions that we can draw, arise from a sequence of closure and permeation steps, where gamma I is the ith cell, we close it at the 0th step under the sentences, so we close it logically whenever our background logic is, at the first step, and then anything that's in the permeation relation from other cells to this cell, that the other cells bear to this cell, right, that's derived at the nth step, right, together with the nth contents of gamma, are put together, and then you close again. So you close and permeate, close and permeate, close and permeate. Eventually, maybe you come up to a final result. Maybe you could carry on indefinitely, getting more and more and more, but as long as it doesn't blow up in your target chunk, and you can arrange it so that none of the other chunks blow up too, you can always transform one that has that flaw, if you like, into one that doesn't. The upshot is that each chunk can contribute to what we conclude in the target chunk at the end of the day, the end of this sequence of closure and permeation steps. And what I want to say is that this gives us a kind of answer to Belmont's query.
I'm sorry. Can I ask just a quick
Sure.
question about the theory? Is there a theorem that shows that you can always do this transform chunk which is problematic to
That blows up into, yes, yeah. It's in a paper, I think, that I published in 2014.
Okay, just one.
I should actually, I might even have it on the hard drive in my bag. Well, no, actually in the hotel. Maybe tomorrow.
That was on the. Thank you.
So we don't propose any kind of heterodox formal logic. We don't need a separate logic. We could have classical logic in all these chunks, or you could have another, but we're not looking for a strange paraconsistent logic here. And so we don't have to be all that fussy about exactly what logic we find ourselves committed to. It will, of course, make a difference in general, but it might not make a major difference to getting the result that we're actually interested in getting in the target chunk at the end of the day. So we don't need to claim that scientists implicitly rely on some such logic. Right? That logic is in the back of the mind of working science, which has always been a pretty implausible hypothesis. That's one of the points of Belknap's concern, that he's raising with that question. All we need to do is provide a chunk and permeate structure that captures the arguments that the scientists use while keeping inconsistencies isolated, and especially out of the target chunk. And what we've, in a sense, modeled is a class of, or a collection of patterns of reasoning which are allowed by the CNP structure. And so long as those cover the arguments that scientists are actually endorsing, we've got a pretty good picture of what they're doing without having to be, as I say, too fussy about what logic exactly lies behind it. So on to pluralism. Pluralism, I like the metaphor of a patchwork quilt for it. Right? Science has lots and lots of different areas of interest, and different scientists work on different things. And insofar as a picture of the world emerges from that practice, some of these patches are a little bit attached to other patches. Some results from one area might be transmitted or relied on in another area, and so on and so on. So there are threads connecting them, but they're individual threads. They're not integral pieces of cloth together. The whole thing isn't a solid piece of cloth, continuous. If we accept that science really doesn't offer us a unified story of the world and everything that's in it, I think that frees us to focus today on what we see when we look at science. We're not thinking about science as it might ideally be. Some of us might be interested in that question, but it's a kind of a remote question for someone who's actually interested in what it is we're looking at when we look at the scientific endeavor as it now stands. So does science aim at a true theory of the world, or only at a theory that meets in weaker conditions such as empirical adequacy? That's a standard question that people raise when they're concerned about scientific realism. But again, when you raise that question in that way, this is an argument about what an ideal science would be like, what the sort of finished product of science would be like. So I think that some of the standard puzzles about whether we should be scientific realists or not are end-of-the-day puzzles, and I don't find them particularly interesting either. I really want to be focused on the science that we now have. I think it's a very interesting phenomenon, socially and intellectually. They don't explain, so these arguments don't explain why science as it is motivates such debates. Maybe it does, and maybe there are explanations for that, like some of the strange entities that we posit in quantum mechanics. And we say, okay, well, how does that relate to thinking about the end product of science someday being the truth about the world? But it again, I think, is a distraction from science as we really encounter it. So I think more broadly, philosophers have often treated the successes and the limitations of science as motives for pursuing very ambitious, philosophically, metaphysically ambitious, or perhaps epistemically ambitious questions about ideas of truth and knowledge. And I think I'd rather be more philosophically modest about the lessons that science can teach us and what we can learn about science, and then look for other kinds of lessons to draw from what we see in science. So a contemporary focus, we focus on science today, that might actually lead us to understand better the aims and successes of science than we could find in attempting to answer or focusing on end-of-days questions. So I propose that we focus on more immediate questions about how current scientific reasoning actually works and what the proximate aims of scientists are in their work. So there is obviously, and I think a lot of people acknowledge this, a sharp contrast between the diversity of science as we encounter it today and the philosophical dream of a kind of unified science that some of the positivists in particular imagined. We use a wide variety of tools and methods to produce the models that we apply to the world and that we reason with. The results of science are often exploratory, and the reasons that people engage in getting to these results are often a stretch, right? They're often not terribly rigorous mathematically. But some reliably approximate the observed results or results that we found, and later find perhaps that they follow from more precise calculations that apply a principal theory, a better, more finished, more polished theory. And we also know, of course, observational methods vary a lot in reliability and precision. And some are exploratory, others are well established. And so I think of science as it actually takes place in the field to be a pretty rough and ready business. And in particular, as Wimps has emphasized, heuristics are sort of in the air continuously. You're trying to find shortcuts and methods that get you something that you can then maybe later wrap something more substantial, a systematic theory around. So I want to get away from logical and metaphysical idealizations. I'll skip through this fairly quickly. I think that the success of science as we know it goes beyond anything that prior experience and philosophical reflection, say prior to Newton, gave us any reason to expect or suspect would happen or emerge. But even now, I think the philosophical response to science is shaped by these long philosophical traditions that predate that accomplishment and that set a very different kind of bar, but I think the wrong kind of bar for how we ought to think about science and how we ought to understand it. So what do we do? Chunk and permeate is an approach that solves the problem of dealing in a non-trivial way with inconsistent premises without eliminating the inconsistency, without requiring a formally paraconsistent heterodox logic of some kind. And it gives us a nice straightforward model of reasoning that actually follows, to some extent, the path of reasoning. I think it actually makes a pretty good account of Bohr's theory and reasoning in the old calculus. And a number of other interesting examples in Dirac function as well. So I think inconsistency is one of the things that's always in the back of our minds, or should be, as a risk when we're doing any kind of serious, large-scale epistemic work, where we have a very small, well-regulated collection of concepts, as we sometimes do in mathematics. Maybe we can be pretty confident that we're not going to get into trouble. But when we go out into the world and try to put together concepts that are going to fulfill the demands we have for reasoning successfully about events in the world of one kind or another, I think it's extremely difficult to expect consistency from the start, at any rate. Maybe you can accomplish it or resolve differences in the end. We have science ranging across topics, processes, orders of magnitude, and the concepts are very heterogeneous, and we have an immense variety of phenomena to try and encompass. And we know already from the philosophical tradition how many paradoxes and conflicts between just very simple aspects of common sense description of the world, like puzzles about distance in space, and whether a finite distance could be made up of a whole bunch of infinitely smaller distances, as in some of the Zeno regress paradoxes. It seems to me that it would be odd to expect that at any given time when we're doing something as complex and rich as science, that we would really be able to pull back and say, oh, here's a consistent story of what we now think. I don't think we should expect to be able to do that. We already know you can't prove arithmetic alone consistent without actually blowing it up, assuming that you're doing it classically, or something like classically. In the history of science, we see that inconsistencies arise and they're dealt with in a non-catastrophic way. If we don't exploit it to draw arbitrary conclusions, then we don't draw arbitrary conclusions. We don't ordinarily exploit naive truth talk to infer arbitrary results, except for philosophical effect. Right? We perform the act for our students to sort of show them just why they should be troubled by this, instead of just say, oh, go away. You know, not that interesting, really, to most people. Philosophical paradoxes turn up whenever we push reasoning and systematization to these kinds of limits. When we try to press the matter, we get into trouble on a regular basis. And I thought I'd try to wind up with just a few remarks about different ways in which inconsistencies do arise. There are local inconsistencies where you have a small, closely linked collection of concepts, true paradoxes, just a very easy example of that, or Zeno's paradoxes, or so on. Paradoxes of infinitesimals, pragmatic paradoxes like I'm dead, I'm asleep, or darkness, there could be an unobserved world. These are trouble spots for familiar reasoning patterns that apply certain concepts or claims that we find reasonable to accept, and then we say, wait, that's kind of troubling. And the very same patterns of reasoning that are involved here are generally treated as perfectly acceptable. But we see that in the right way, if you just put the right twist on it, that same habit you have of accepting certain kinds of patterns of reasoning leads to trouble. Then there are global inconsistencies. These arise when you have concepts, commitments, or evidence that are drawn from separate areas of discourse, and they come into a conflict with each other. These are too rich for philosophers to just spontaneously come up with them. Maybe I can be refuted. Counterexamples are welcome on that. But in general, the ones I've thought of and been able to think of just don't come up in philosophical reasoning. They happen when principles that we've had lots of success applying in separate concept and contexts turn out to conflict when we apply them to reason in what seem to be perfectly reasonable ways. In some contexts, they both apply to. So late 19th century attempts to model black body radiation. What do we do here? Well, we've got thermodynamics, we've got classical electrodynamics, let's get to work. And if your name is Planck, that's what you did. And the anticipated theoretical unification, this is a big target. This was one of the big fish. This is one of the sort of final winding up of physics feats that would basically finish the business, at least in the eyes of some in the field at the day. Another example would be present-day tensions in quantum mechanics and general relativity. So these are global inconsistencies. They don't arise easily from just a few everyday or even just a narrow collection of scientific concepts, but we start putting things together in a large-scale way and we run into trouble. And another kind of case arises when you get conflicting answers to a question from different investigations. So here we've already heard today about 19th century debates about the age of the earth, so I won't go too far into that, but that's an interesting example. Darwin, as I said, had a pretty good calculation based on sedimentation rates, and it was generally agreed by most geologists at the time that, you look at the sediment, you can see it being deposited, you can see very, very similar patterns in the rock record, you can measure the depths, you can say, look, if this were to have happened much, much faster than it now does, it seems really unlikely that it would take the same form to the degree that these historical formations take vis-a-vis, contemporary sort of lake limnology results. When you take a core from a lake bottom, or a pond for that matter. So you run up against an inconsistent conclusion, drawing from completely separate sources of scientific authority, both of which seem perfectly legitimate, perfectly well justified, and there you're in trouble. There are three ways in which we can get into this trouble. When we're faced with inconsistencies, what do? We don't just give up principles and concepts. We don't just turn our backs and walk away. Although I suppose mathematicians in some cases would say, okay, listen, not that theory, some other theory. But certainly in the empirical sciences, we tend to push ahead to try and get some hint as to where we were wrong in the first place, where the problem lay, perhaps. And perhaps sometimes we persist for longer even. We avoid the danger zone because we find the theory works reliably despite knowing that there's a danger zone. We, as philosophers, be careful about uses of true and false in certain contexts, known bad applications. Sometimes we look for systematic ways to avoid dangers. We adopt new concepts, rules, or theories that might eliminate them altogether. That's when we resolve them, but of course, that's the kind of prescription that we can't simply fill on a given day. That's the kind of prescription that maybe gets filled eventually, if we're lucky. But there are lots more pragmatic responses, including proposals for how to carry on in the meanwhile. And I think, given the perspective I have on treating science as it is rather than as we might ideally want it to be, the fact that these things often do get resolved doesn't resolve the problem that we actually face when we're in the middle of things and dealing with it. And so we get proposals like chunk and permeate or Norton too, also, without being as systematic as chunk and permeate, tries to find ways to resolve the inconsistencies that are arising. And I wanted to close with one new kind of example, which in a sense theoretically isn't troubling at all, but it does involve a practice in which we reason with inconsistency to get results. What we do in climate models quite often is take a global circulation model and combine it with a regional climate model with higher resolution nested inside. And that gives us higher resolution of certain features that you just will wash right out. The Great Lakes in the global model generally wash right out. It's just continental across the whole of North America. Well, the Great Lakes locally are a very big influence on what the weather's going to do. So if you want models that are going to tell you a little bit about what climate change might do to your weather, I don't know, in eastern Quebec, you really would like to deal with the Great Lakes in a serious way. So you get something like this in the GCM, and you can see the large-scale grid here, and there is an RCM nested within it with a much smaller grid. So here we're going to be calculating values at points much, much closer together, which gives you much better resolution. And you're more likely to pick up patterns in local weather if you do that. You can do it in two ways. You can nest it one way, where the RCM nest is driven by the GCM that it's embedded in. You can do it two ways and have RCM results also feed back into the GCM and modify the output of the GCM. And sometimes you have moving nests which roll around. If you're trying to track a hurricane, this is what they do. They have a larger model, larger grid model, and then a smaller grid model covering the storm. And you run the two together and drive one with the other and vice versa. You can just vary the scale of the grid, but that's very messy because you can't just vary the scale of the grid. You've got to change all your parameterizations and subscale processes. So that's kind of interesting. Actual practical applied physics. The underlying physics, there's no contradictions in any of the underlying physics that these people are using. It's very conventional stuff. But the RCM and the GCM are producing conflicting figures for values of pressure and temperature and humidity in the RCM nest zone, because the GCM is running on the whole planet as well. The correction, so what they do is they correct the results for the boundary cells of the RCM so that the GCM drives it. And if it's two-way, then you also correct values from the GCM back again. And you usually have a sponge zone too, because you can't just change them right at the edge of the RCM and you get shock effects, pressure waves and things. But what we're doing here is we're reasonably consistent information. We have two sets of information about temperatures, pressures, etc. in the RCM nest region. And what we do is we forcibly change some of them and then carry on with that inconsistency still there in the model, and we make good use of it. And I'm not going to go into the details here, but in the paper where I actually did this work, presented earlier this summer, I gave a fairly detailed account of a chunk and permeate picture of what's going on here, just showing how different values are basically overridden systematically in both sides in the two-way nesting case. So I'll go through, I think, how much your time?
You have 15 minutes.
15 minutes, okay.
15.
15. Okay.
3 hours, right?
50, you haven't even started.
No, I'm going to stretch it and take it easy. So at every time, here's the two-way nesting case. Why don't I talk a little bit about that? At every time step of the GCM, which is a longer time step typically than the RCM, every time step of the GCM, results in the GCM for grid points in this boundary zone are used then to adjust the values of parameters to get grid points in the other cells of the RCM. So you just force values that are inconsistent with what was generated by the RCM, and then you apply the same apparatus, the mathematics of the RCM plus the other values that haven't been altered, to calculate subsequent grid, subsequent time steps. And the values here are also adjusted in the two-way nesting in response to the values assigned nearby grid points to the RCM. So again, you've got contradictory results, and you just say, in those regions, and you just say, no, we're going to change them so that they accord better, because we think that's the way these two separate models should interact.
Is that happening sort of in real time, that you're adjusting the data? So, so your model says there might be a rainstorm, and then you see there actually is a rainstorm now in this area. So.
Well, that's what you do when you update actual weather models.
Right.
But here we're projecting into the future.
Right.
So the only feedback that these models are getting is just from the other model and back and forth. So the chunk and permeate picture comes through fairly clearly, right? Because what we do is we wipe out the values for the boundary cells and we replace them with values that we've deliberately calculated based on the values we found in the GCM. And then we go through and make a similar sort of adjustment to the values in the GCM. And if we're rewriting different values, then we're actually contradicting what we had said earlier as the product of this model, which is an inferential structure. So there is a need to sort of say, okay, we actually are dealing with inconsistency here in a very constructive way and not, as I say, in any way a metaphysically troubling sort of inconsistency, but just a conflict in the data that we need to resolve in order to make these models do what we actually expect them to do, which is give us some sense of how regional climate might respond to changes in the surrounding global climate. So we have algorithms to tell us how to rewrite these things. But those algorithms, as I said, are taking data in and then putting contradictory, incompatible data back in place of it. So the aim here is partly to produce an account of possible changes in regional climate due to global climate change, and then that can inform planning for adaptation measures. And one of the points here that sometimes people don't appreciate, the point is not necessarily to get it right, but to estimate risk and potential risks. And so, for instance, you might be interested in maximum stream flow issues if you're concerned about flooding, and you're dealing with a government agency that's involved in dam building or other sorts of water management. Your cities need to be warned about possible needs for greater ability to get water off the streets. And in those applications, the subsequent states of the RCM are constitute the target chunks. Right? That's where we're drawing our conclusions, because that's what we want to use pragmatically to reason about possible policies as potential prudent responses to the circumstances. In the two-way model, or the two-way nesting, the GCM responds to input, and we can treat the GCM in that case as the target chunk. And we're trying to see what having a more detailed picture of what the regional climate does contributes to refining or revising the expectations that we were initially getting from the GCM. And again, that's something that could be an important and valuable conclusion. And the reading then, I think, this is one lesson about CMP that I think follows here. In particular, how we identify the target chunk is going to depend on the applications that we have in mind and the kinds of conclusions that we're looking to draw from the system. We can be running the same system and using it in different ways from a CMP perspective, where we have a specific list of target chunk. So I'm nearly to the end now. When we think about reasoning and logic, the models that we build focus on role consequence relations, reflexive, monotonic, transitive, relations on language L, and the consequences that follow from some ensemble of premises or the sentences in the closure, gamma under the consequence relation. And we model reasoning in general in this context by drawing on that consequence relation, some consequence relation or other, and we say reasoning from gamma to sentence, something in the language, some sentence in the language is correct if and only if S is in the closure of gamma under B dash dr turnstile there. These consequence relations provide systematic normative models of reasoning. They endorse reasonings that cite the members of an ensemble of gamma's premises and derive a member of the closure of gamma as a conclusion. We endorse those as correct. But I think real human reasoning, and this is getting back to Belknap's question that we started with, real human reasoning is very, very selective. We only follow some of the paths. We only draw some conclusions. As logicians, we might occasionally draw some of the ones we wouldn't normally draw just to illustrate that that's a consequence too. So some long conjunction, maybe repeating the same atom over and over again in the conjunction. You don't see that, we don't do that, but the consequence relation itself, of course, allows it. And this is where I think CMP makes sense, or one reason why CMP is intuitively appealing to me. The inferences we make, typically, the real inferences we make are exploratory or targeted or directed, they're aimed. There are certain kinds of conclusions we have an interest in. And we structure our reasoning quite carefully to try and make sure that we do a pretty good job, especially when it comes to getting to those conclusions. C&P structures cope with inconsistency when we have it by isolating the conflicts, but the sentences in our sort of background kit, the overall set, can still contribute to the conclusions we draw via this sequence of closure and permeation steps. So in a sense, what we're doing here is an amped up version of that selection of pathways of reasoning, paths of reasoning that we follow here are really specified and constrained within C&P in a way that they're not under a normal logical consequence relation. Dividing the commitments amongst the chunks allows us to provide simple models of constrained reasoning then with inconsistency. And the permeation relation is what ties it all together. So every member of the collection of your commitments contributes to the conclusions we get. And then back to Belknap's question, another aim of the work has been to avoid imposing a specific logic as part of these models of constrained reasoning. Because, as I say, when we look at science in the wild, as it's done by scientists, they don't typically state their logical preferences. They don't typically have any. People say, oh, maybe classical logic. But in a way, I think that interpretation reads too much into it. I'm not sure that it's really classical logic. All you have is the reasoning, and the paths of reasonings they actually do follow are a very, very small subset of the paths of reasonings that you could build out of a classical logic or any other form of logic. And I think in approaching it this way, we're providing an answer to John Norton's insistence on content-driven rather than logic-driven approaches for dealing with inconsistency, because we focus on changing how the content is actually dealt with or applied in the course of reasoning rather than on an appeal to a background heterodox logical system. So I think what I like about C&P, and one of the things that I like most about it, is that I think it occupies a middle ground here. Maybe that's a Canadian thing. Emphasizing closer attention to patterns of reasoning that are actually employed and accepted by scientists, and using C&P structures to show how reasoning can avoid trivialization without appealing to any specific weakened consequence relation, which faces always Belknap's question. And so the conclusions of just these closure under consequence gives us a systematic account of cognitive commitments, but we can't and don't have clear, firm commitments at the start. We're always in the middle of things, ready to revise. Locally successful patterns of reasoning are identified, and then gradually systematic theories may emerge if we're lucky enough to be able to build such things out of these local reasonings that we found seem to work. And the C&P structures model that kind of reasoning while avoiding any kind of logical closure operation at all, except locally, and even there, I think that's probably, if you like, a crudity in the C&P model. You're not really following the actual path of reasoning. The closure operations are kind of a convenience for the machinery as we're applying it. When the conclusions that we reach work out, we can work to extend and systematize the reasoning and maybe even eventually come up with a theory that doesn't require this kind of prevention of cross-contamination, if you like, of your different collections of premises. And I think on the larger scale, scientific engagement with the world isn't producing anything like an integrated and systematic account in which all our observations have their place. I have trouble imagining what such a language would be like. And finally, this treatment of nested climate models shows that we can also model complex reasoning that's motivated by calculational intentions, by certain kinds of aims. As I say, it's slightly crude because we're still closing within the cells, but at least we're constraining the path that reasoning follows in a way that hardly resembles real scientific reasoning. And yeah, that really is the end of it.
Michelle?
Yes, in answer to Moisés' question at the beginning, you said that there was a theorem stating that any form of reasoning can be, what was it, that any trivial?
Any chunk which was
Trivial can be removed. Basically, you remove it, and as long as the whole thing doesn't trivialize, right? but that one does. You remove it, you pass on to any of the other chunks that it has permeation relation to, everything that's allowed to permeate, right? And then you're going to get the same results in the conclusion chunk. So you just delete that chunk effectively and replace it with these others, which on the assumption don't explode.
But say that, so can you just go through the nitty-gritty of this? So let's just do a proof of P and not P, therefore Q. Any of those proofs through disjunctive syllogism, I don't care. And if we do that in natural deduction, and then can you chunk and permeate it for me?
Something like that, if it's not.
Can you explain a bit what is going on?
Okay, well, what I did was I should probably just put these steps in individually.
Not P or premises, then you do an and introduction, so then you've got P and
Right,
P.
but I take not Q as a hypothesis, where
Right,
Q is some
okay.
arbitrary
Okay,
proposition.
good,
I can join the two, that gives me the contradiction,
Yeah.
right? And since this is my hypothesis, I get to say, no, I get to negate
well,
my
hold on, because
hypothesis
you need
now.
some step, no, you need some. Okay, all right.
But this is just a classical proof.
Yeah, that's just a classical proof, yeah.
Okay, so say that's one of my chunks.
Okay.
Okay, so say I'm
So
I'm
we've
I'm a
got
tricky
C1.
scientist, right? So as a tricky scientist, I want to get this article published. And I think I'm going to be able to fool the reviewers by working through an inconsistency and they're not going to spot it, all right?
Well, this is
So I
not
actually-
gonna help.
Why not?
Unless your reviewers are sort of,
No,
don't
they
get it.
don't actually check the proofs a lot of the time.
Yeah.
So, so say I actually more or
Okay.
less do, I mean, I disguise it enough that they might not see it,
Okay,
okay?
Right.
So I actually did, secretly I used this, and I disguised it sufficiently in my article, so it passed review, passed muster.
Right.
And then my whole conclusion in my scientific experiment is, that's okay.
Good.
So now
so
what you
I've
do.
got Q here.
Right, right,
Okay, so
so
I've got my arbitrary conclusion.
that's right. So now how would you treat this with chunk and permeate so that it's?
Well, suppose that we take the background logic in each of the chunks to be classical, right?
Right.
So we've got a chunk in which we have the premise P and a chunk in which we have the premise not P, right? Well, to avoid getting an arbitrary result, right, what you need, obviously enough, is that at your target chunk, down here, T, there's no pathway in your system that allows you to get both P or perhaps something else that you derived previously from P and not P by combining them. If you keep these isolated, right, then that's what you're preventing in effect. One or the other of those pathways. You could get P, you could get not P, right? If you're just trying to avoid explosion. But you wanted to get
I want
Q
Q,
through it.
yes.
You want to get
In
Q.
my
Well-
sneaky paper, I got
well,
Q.
Children permeate's supposed to stop you getting Q. So,
It
you
is,
know,
and that's what I'm
yeah.
asking, so why would it,
How would it do that? It's precisely because these two things are isolated up here in separate cells. And unless you allow them each to permeate into either the same cell or one to another cell that then permeates into some cell where eventually not P arrives as well, right? Unless you allow that in your permeation structure, then you never get to combine them. Here, the assumption is that any premise you've got can be applied at any point in the derivation. CNP says, no, you can't just apply it anywhere you please. We're interested in certain paths through the space of reasoning, and that's not one we want to look at for this very reason.
Okay, and how is that different from? So what was the result again?
I just asked, he, at some point during his talk, he said that if you have a chunk which is not well behaved, then you can just take it from the reasoning and you can carry on reasoning without getting any.
Suppose you've got a
Should that be a
non-trivial
trivial
structure.
joint from the very beginning? A trivial, like a trivial premise, an inconsistent premise from the very beginning, is that what is meant?
Even there, I mean, the point is, if your permeation relation is restricted enough, right, you can have a cell blow up, and the only thing that comes out of it is Q, for some sentence Q.
You say I want that.
So,
So
what you can do is something like this. So you're trying to, you're saying, let's have a cell where we've got P comma not P. When we do the closure, one closure operation, we wind up with Q in there. You say, but Q, right?
Right, and I'm just letting Q permeate.
Mhm.
Is that okay?
That's a CNP structure.
Yes,
It's got a non-trivial result.
right.
It's not an interesting one. This is not a general logic that's meant to prevent all sort of bad paths of reasoning from occurring.
Okay,
It's meant to model successful reasoning when you don't want to put all of the things that you're actually saying in the course of the reasoning together because they're actually inconsistent and would, under, say, the background logic that you're assuming, actually trivialize your results.
okay, right.
Ottavio had a question.
Yeah. So, in a way, I wonder if the very structure of CNP actually requires some logic, right? So, for example, when you say, look, I have P here, I have not P there, as some chunks, but nothing here requires me to
Combine
them,
those, yeah.
right? So, isn't that some form of non-adjunctive, right, logic?
It's weakly aggregated in that sense, yeah. No, it's
So-
related to weakly aggregated logics.
So, and I wonder if there aren't other, as you work through the reasoning, right, in effect, there is all kinds of logical machinery being involved in the very way in which chunk permeated structure.
Yeah, you do have consequence relations in here, but my point is that in a sense, just as I think in science, we don't tend to specify a particular, characterized formal consequence relation when we're doing scientific reasoning, here as well, right? You can bring that on board and have inconsistent premises and use this kind of limited permeation strategy to prevent trivialization.
Right.
So your background logic might be classical. You don't have to assume that. You can just allow inferences that people would make if you presented them with them right there on the page. Said you buy this, yeah, okay. Well, then that would be part of how you end up closing each cell at each step of the process.
Right, but then I wonder if this is not actually a form of logical pluralism, right? In effect, where you have your chunk structure as a logical space of some sort, right? And then you have regions of that space that are ruled by certain logics. And of course, you can adjust and choose in accordance with whatever criteria that are relevant. What that is.
It's not incompatible with that kind of pluralist picture. You can have, in principle, different consequence relations to different cells. We've assumed so far in the applications we've tried, just a background and typically a classical consequence relation is the background. But for a lot of these purposes, it doesn't make much of a difference because as long as you get the conclusions you need on to further cells, you can keep the inconsistency isolated and still get the result that you want to get, as Bohr might have done regarding the frequencies of observed radiation coming out of hydrogen atoms under certain conditions.
Right. So, yeah, because maybe it's a notational variant, or it's a sort of a, tamed logical pluralism, right? That is, look, we're operating with classical logic for the get-go. If other things are needed, well, when they bring that in.
There's plenty of room for that, but the point is we don't, and this is both a response to Norton and a response to Belknap, we don't have to posit some particular logic, which always seems implausible when you look at scientists actually reasoning.
I agree, and I like that. And can I ask one other question? So about the climate models. I love the examples. Those are really interesting, and I think climate models are extremely rich to think about philosophy science. One issue that often comes up, at least when I talk to my colleagues in the meteorology school about that, is they point out to the following situation. There are two big trends currently. You have these people who want to go the higher resolution, the better it is.
Bigger computers.
Yeah. And they basically force you those out of competition if you just don't have access to the machinery. Because you cannot run these models unless you have really extraordinarily powerful computers. Right? And you have a different group of people say, look, don't overdo it. We can get predictions that are pretty good for all practical purposes with models that have far less resolution. It's not that these models get you.
It depends what kinds of results you need.
No, that's right.
Yeah.
But that's part of the choice. Right? So for a number of applications, you can consider a little square over Florida, and that will be just fine, right? Of course, for others, you may need, a bunch of squares.
Yeah, regional weather planning probably requires a little more detail.
Yeah, exactly. But really, that's a pragmatic choice, right?
Yeah,
and then you have a situation where that kind of constraint will bring in your choice of the appropriate models that you use.
Right.
So then there's also the example that often is pointed out. Some of those models are not even empirically adequate, right? And they are known not to be so. Right? And
so there are known biases and so on, but
and look, again, depending on the kind of problem you want, it's fine.
Yeah.
You can even work around with those ones, and sometimes they work better. They're cheaper, easier to handle, require less, and you may say, yeah, that's just fine. So then the question for you is, now, once you get into these kinds of choices, right? What do you think, how should we reason about selecting these things?
Yeah. I think just from the way you asked the question, this has got to be something that concerns pragmatics and goals and values like reliability, and particular values like reliability vis-a-vis quantity X in region Y. And if you have answers that you can supply regarding, on the one hand, the evidence about these climate models, what kinds of results they produce, and answers you can supply regarding what quantities you're most concerned about, or what quantities you need to have some reasonably reliable, and you can state those boundaries, results for, right? Then obviously you can make a reasonable choice of models. But I think in all of these cases, and more generally in a lot of science, we're better off thinking about the preservation of reliability. Even when we talk about empirical adequacy, what do we mean by that? We mean, well, we've got some practices of measurement that we rely on to a certain degree. And when we talk about empirical adequacy vis-a-vis those practices of measurement, we want to come within some bounds, right, of the values that we would actually expect to observe given these observational practices. And we can have a lot of practical real-world evidence that a particular class of model is capable of producing those results. And truth is long gone at that point.
Okay. There are many questions, so I wrote you all down in the order in which you raise your hand. So, Didier, you had another question?
In a sense, you confused me. I heard Graham talking about this before the paper was even published, I think. But, for example, you said at some point that you can run the same system and use it in different ways. Now, suppose you have a premise set, or a specific theory or whatever, and you apply it this chunk and permeate mechanism do it. Is there a unique consequence set that you will arrive at in the end? I thought so, yes.
This has been the way in which it's generally explained.
To suppose you have classical logic as
And I think this is fairly true to most cases where we're dealing with scientific reasoning. In the papers that I was looking at when I came up with this particular application, right? Most of these are people working for the Uranos consortium in Quebec. And what they're doing is they're providing practical guidance to the government about particular issues. So there'll be a paper, for instance, about maximal stream flows. That's an actual example. And so what you're looking at is peak melt rates in spring. So you've got measures of snowpack accumulation that you want to be calculating. And you're going to have a cell where these results emerge. And that's going to be in the regional climate model, right? The regional climate model cell is where you're going to get the results that tell you about peak stream flows. But if you're looking at the impact of the detailed picture of the regional climate that you get from the RCM and trying to say, what difference does that make, say, in the region of the GCM surrounding that regional climate, so that maybe we can modify the GCM results to get some predictions, to more reliable predictions about this broad area surrounding the regional climate model, then that becomes the target chunk. Graham, came up with that terminology, actually. That's his word, target chunk, or phrase. And his notion was that these were fairly directed reasoning processes that we're trying to model. And my point here is just that, look, depending on the purposes and aims that you bring to the enterprise, you could build a very similar, or you could build the same chunk and permeate structure and be reaching the conclusions you're interested in a different chunk. For you, it's the target chunk for this model.
But does this mean that, suppose you know that classical logic is the underlying logic, that you say now I start a mechanism and the parameters are on the one hand my premises, my theory,
as distributed across the
and then
chunks.
on the other hand, the target chunk. Target chunk, I'm sorry. I'm bad. Given these two, then it is deterministic or not?
Yeah, it's going to be deterministic. The idea is, in the more logically oriented model that we first invent, right, that you get to the end of the day where you've done all of your permeations. But most of these models will stabilize after a few cycles.
And that very small, absolutely last question. You seem to, you presented it as if the mechanism is unique.
Well, that's an interpretive challenge. I think we face that challenge whenever we try to produce a logical model of some bit of scientific reasoning. We really do have to make choices, for instance, about the background logic and so on. So the assumption is we've built a model that's meant to capture the reasoning these people are doing. In this context, we're probably going to use classical logic, classical mathematics in the background of each chunk to be part of the calculational sort of engine.
No, but independent of the background logic, you consider the mechanism as unique. There are no alternatives there.
I
If we
suspect
look at logics, we have affinities of logics in all directions, and even the things we did in Ghent with this inconsistency adaptive logics or other adaptive logics, we have whole.
Combining Russian Lander with weakly aggregative.
But you seem to have.
Well, we have a shared structure. You can build different models with it by varying how you divide the premises up, right? If you're looking at a particular reasoning practice, presumably you're drawing on that for concrete evidence of how people were combining premises to reach conclusions, where those conclusions went in the reasoning algorithm that they're following, and what they were combined with subsequently, and that's what's going to guide your construction of this thing.
Okay, Maria, you had a question?
Yeah. So mine will be a very silly question, but because let's say that I believe that chunk and permeate tries and succeeds at explaining or describing how scientists use reasoning, at least when facing inconsistency in science. And let's also say that I believe that sometimes scientists do not know that deep their theory, and so they can provide an hypothetical division between their theory when they face inconsistency, and then they can say P is in chunk A and not B is in a different chunk. But suddenly they realize that not B is not in that exact chunk, or it's not coming only from the prepositions that are included in that chunk. So they have to do something about the division that they have proposed.
Right.
And I am not sure about if chunk can permeate in the way you and Graham have provided, can recuperate that movement. Let's say that you don't have to do it, but it would be interesting to recuperate all that, because it seems something natural that scientists do when facing inconsistency, rather than to provide different models in time 1 and time 2 and time 3. Can chunk and permeate do something like that?
Well, it provides a framework in which you can do that in a way that's responsive to what the scientists have done. And the idea is, look at what premises they used, at what steps in their reasoning, look at where they drew those premises from, and look at in particular where they drew premises from in order to arrive at the sort of final conclusions they're drawing, whatever those might be. So if we're talking about Bohr's model of the hydrogen atom, right, we're interested in the conclusions regarding the frequencies of light that are emitted or expected to be emitted from a sample of excited hydrogen gas. Right? So if you take that then to be your target chunk, right, you look back at Bohr's reasoning, right, and you look at where certain premises were used, and you, in this case, right, wind up with a chunk in which these frequencies are specified, where you don't have the model of the atom itself, right? And as a result, where these frequencies are described, the target chunk, right, is actually the chunk where you have a classical theory of electromagnetic radiation, you have CED, and that's where you interpret the results of the model, because that's where a spectroscopist gets some advice about what she should go looking for if she wants to test Bohr's theory. So it's very much in the pragmatics. I don't know if that's addressing the question you're trying to ask.
Yeah, but it still seems to me that you can satisfy the target chunk with different combinations of the divisions.
Possibly,
of the chunks.
yeah.
So
we're guided by, in this case where you're applying the model to an actual example of scientific reasoning, as I think in general we have been. The point there is to try and sort that particular reasoning out. So it's got some premises, taken all together, those premises are inconsistent. You look at the course of the argument by which they arrive, and you say, okay, at a conclusion, like Bohr's conclusion about frequencies of light emitted by hydrogen atoms, and you say, okay, that pathway involved applying these quantum mechanical limitations to model states of the stationary states of the hydrogen atom, and to calculate energy differences between those states. And then Planck's rule comes in also in that context to give you frequency numbers, which there are not necessarily interpreted. They've got the right dimension for frequency, but they're not necessarily interpreted there as classical electrodynamic radiation. Then you permeate those numbers into a cell where you've got classical electromagnetic theory. Those are read as frequencies of light, and you turn it over to the spectroscopists to go looking, and lo and behold, they find what Bohr predicted. And in fact, when he was able to correct one thing that was outside the experimental limit, I forget what it was, but it was a particular line or series of lines that was out of position enough to say there's something not right here. When Bohr compensated for the fact that the difference in mass between the nucleus and the electron was actually finite rather than infinite, as in the original model, and got the right frequency, resolved that difference, Einstein's response was, well, then Bohr must be right. Somehow. But Einstein, I think, said also that he could never have constructed a theory that way.
Jochen?
I really like the idea that you want to explain successful actual reasoning. But for me, there seems to be some kind of tension if you use the CMP approach for that, because probably I'm missing something, but it seems to me that you can only say something about the CMP structure until at the moment that the problem is solved. That you know how to do the chunking and how to what the correct permutation relation is. And so, for instance,
yeah, it's not a normal consequence relation where you have a set of sentences and there are consequences that follow from it. You don't know the consequences until you've actually built the structure and populated it with sentences in various chunks.
Yeah, but in this case, for instance, with the P and not P, it's clear that P and not P should not be in the same chunk. But in interesting
Assuming your
cases,
background logic
not,
is classical anyhow, but yeah, that's going to be a useless chunk.
In interesting cases, it might not be that obvious how you have to do the chunking.
Right. No, that's going to be a practical problem. Yeah.
Can you also explicate that type of reasoning? The reasoning that...
well, as I said,
what reasoning?
The reasoning that scientists perform when it is still not clear where the problems are located and how to handle them, and where contradictions might arise, and how to say, well, I can...
well, I think the idea I would have about...
chunks are so and so.
I would say, hypothetically at any rate, when scientists are doing this, they're trying to be creative reasoners. They're not working with a well worked out theory at all. They're working with premises that are available, if you like, in the field, and they're aiming at a particular topic, and they're trying to get some useful results about that topic. And so the reasoning that they're doing, as I think, in science in general, a lot of reasoning we do is very exploratory. It's not systematic. It's not, okay, we've got these premises, now let's see what follows, in the way that a mathematician might do. She sets up some axioms and says, let's see what we get.
I agree with the exploratory part, but in your chunks, you mentioned a couple of times that it can be classical logic in every chunk. But if it can be classical logic, then you have to make sure that every chunk is consistent.
Yes, right.
That might not be clear without reading about the inconsistencies from the inconsistent chunk. What exactly the contradictions are.
Yes, and this is why you get, this is where, you get, I think this is reflected, if you like, in the postulates that Bohr very explicitly states, and he modifies them through the course of different papers where he writes about the theory. But he's very clear about, what exactly you don't do with the stationary states, right?
But for me, that seems already...
How you don't model the transitions between them at all, and so on and so forth. So I think, in a way, this is actually a pretty good picture of what Bohr apparently was doing, was picking and choosing his way through what premises you could apply here, and what premises you couldn't apply here, and...
Yeah, I agree, but for me it seems that is already at a quite advanced stage.
Yeah.
And I'm also interested in the stage that leads from this very messy thing to these postulates.
Yeah. Well, I don't know. That would be like offering a recipe for doing successful science, wouldn't it? I'd love to have one, but I'm doubtful about the possibility of doing that with these kinds of tools.
Mm-hmm.
But you had a question? No? Okay. Then Michelle had a question.
Well, if we don't have time, then we don't.
No, we still have time. We have 10 minutes.
10 minutes.
Officially,
According to the program, we have 10 minutes.
9 minutes.
Look at the program.
We're
still on track.
Yeah.
At least it's like, shut up everybody, leave the room, right?
I was wondering, CMP structures look like cryptic frames. I was wondering, you or Graham have thought about the model logic associated with CMP structures.
Yeah, Graham may have done some of that. I haven't played with it much because I sort of, as I said, talking to Yoki, I think we're building these things under the guidance of, we're building models of bits of reasoning that seem to be entangled in inconsistency, and trying to find a way of systematically representing them without worrying about imposing some kind of very consistent logic on them. systematically modeling them in such a way that there are constraints that prevent them from arriving at trouble. And the original inspiration was largely derived from Bohr's, effort to specify what you're supposed to do and what you're not supposed to do with atoms as depicted in the stationary states. So yeah, I haven't looked at modal logics for this.
Then Michelle had a question.
Okay, going back to the climate problem, so say my global climate warming model tells me, I don't know, that temperatures are going to increase or something like that over the Great Lakes.
Mhm.
Now, my local one about the Great Lakes or my regional one, tells me that if the temperature goes up, then there's going to be increased flooding. So if I have both of those, then I know that there's going to be increased flooding.
Yeah.
Or
Not your
probably
reliability of,
within my parameters, whatever. Then it logically follows from that, classically, that if I have temperature increase, then there will be more flooding, or okay, I'll put my cards on the table. So here's the inference that I'm playing with, where I'm doing the global and regional and my target, my policy. So I want to worry about flooding or something.
So your target chunk is the regional model where you get those results.
Right, and so as a policymaker, I want to say, look, let's do something about possible flooding, because that's a possibility. Okay, so A and B together imply C. A being the global, B being the regional, C being there's going to be increased flooding in this area.
The C would be a conclusion that actually emerges in B. B would be a target chunk, because this is a result that you're getting by driving the RCM with the GCM as the GCM temperatures rise over, say, a run of 20 or 50 years, right? You find, because you're driving the RCM with those results and temperatures are going up in the regional model as well, and therefore evaporation and so on and so forth.
Right.
You find increased precipitation, you find maybe higher stream melt rates, whatever, and you say, okay, this model is now saying, after being driven by this other model, which is inconsistent with it.
What seems to be the two? No, I'm not talking about inconsistency.
Well, yeah, okay.
But when you have both models together, right?
Yes.
When they're feeding off of each other,
Yes.
then you get C. There's going to be increased flooding in this area.
Right.
Okay. And it might be inconsistent, but it doesn't matter.
Right. It's just
Then it logically follows from this that either A implies C or B implies C, right? This is one of the paradoxes of material implication.
with the horseshoe? Yeah. Well, here we're actually applying mathematics and equations and calculating within the scientific, within each of these cells. So the way in which you're generating this result, right, is by doing that calculation in accord with the chunk and permeate picture.
Okay. So
and now
what
you've got that
so
result,
so
and
that-
you could say,
so
oh,
that-
well, now then
Right,
we
okay,
can,
okay,
we can get
good,
this
good.
logically trivial
Right.
way to that same conclusion.
Right.
But that's only because you actually managed to derive it in this way
Good.
from this model.
Good, okay, good. So what you're doing, right, so the AND is not a classical AND, you're enmeshing the A's and the B's, the global, the regional together in such a way that they can't be just treated as separate, quite separate concepts.
That's right,
Good,
because of this
okay.
exchange
And then you
between the
can't-
two
you
of them.
can't-
Yeah.
Okay, good, nice.
Okay, so we have 4 minutes, and you have.
Yeah, I have
Bless
one.
you.
It's just a clarificatory question on, I take it that you can permeate without using a logical inference to do that, right? So for example, you may have principles about a particular domain you're considering that will allow you to bring two things together. Is that correct? Or you can only permeate modular some.
There's,
Some
in these models, there's a defined permeation relation. right? Where I is the language, right? Or sorry, no, the I is the labels of the cells into L. So all and only the sentences in the permeation relation linking I and J are allowed to permeate from gamma sub I to gamma sub J.
Is that the same
Well, what
relation
are those-
between
So you
chunks,
specify
or is it
in-
per chunk? Is it specified per pair of chunks, or is it for any pair of chunks?
No, it's for each pair of chunks. So what's allowed to
take the
go
first and
where?
second chunk,
Yeah.
then this is allowed to permeate. Given the third and the fourth chunk, these are allowed to permeate.
Yeah.
And that's all
Given
in your
the first
little
and the
row
third,
there.
yeah. And then maybe in some cases, nothing permeates from some chunks to other chunks.
Right.
And basically, you're just trying to, in a sense, get a picture of how the calculation gets done and how it gets done using inconsistent commitments in different steps without conjoining those two to get a trivial result if your background logic is classical or intuitionistic or any other trivializing.
Right, so basically, then the answer is yes, because if, I don't know how you get these sentences, right? But presumably some of those sentences.
It's modeled on the practice, as I say. In Bohr's case, he really was fairly specific about how you go about reasoning with this model, and there was some variation, but the same general ideas were clearly there in his articles.
No, right, but in that case, because he was inferring not out of logic, he was inferring out of physical principles, rules of thumb,
That's right. Yeah.
imposition that he just made up out of the blue. There are all kinds of stuff going on.
Yeah, and it was all, I think, scientifically well motivated,
Right.
but it was extremely creative and bold as well.
Okay. So now, where do inference rules get into this picture, if they do at all?
Well, there is presumed to be a background logic in the chunks.
Okay.
And that background logic, the interesting thing is that the chunk and permeate system can be paraconsistent even if the background logic in every one of the chunks is classical logic or some other explosive logic. And also, to a large extent, as with most logic, it doesn't make a big difference. So, if you're trying to discern what logic somebody's using and you allow for a little enthymeme here and there and so on and so forth, I have no idea what logic I use when I'm ordinarily just out there thinking and talking away.
And there might be several logics to satisfy.
Yeah, there could be several logics. So it becomes fairly robust under shifts in the details of your logical commitments.
Okay, thanks.
Do you have a last question, or but
A very small one. I find it really puzzling. Suppose you start from gamma is a theory, and of course it has even arithmetic in it. Okay, a physical theory with arithmetic in it. But it's clear that you have an infinity, even an uncountable infinity of CMP structures.
Yes.
So
again, the model has to be based, if you're going to justify selecting one CMP structure, it has to be based on the cases of reasoning that appear to be interesting to you, that appear to be cases of reasoning from what look like inconsistent premises. And you're saying, okay, how did they do that? So that it arises from the ground up as a puzzle.
There should be some instructions in the sense, well, I first arithmetic because there you have a schema, of course, and you could say, well, I put all the instances of the schema of mathematical induction, I put them on different chairs. Well, why not? So I have an infinity of chairs. This is complete nonsense, isn't it?
Well, I'm not saying every chunk and permeate structure is a useful thing to play
Do you
with,
have
nor
any-
is every set of
do you have-
premises that we might have.
Do you have any ideas about which structures, which might be more interesting?
So far, we've been trying to take our lead from actual cases where people seem to have done useful work with what look to be inconsistent premises. And so the stuff is motivated from the ground up. As I say, I don't think that this is what was there in the background all along, right? This is a sort of apparatus of the sort that we logicians are roughly familiar with, which can serve to build models of what looked to be pretty interesting examples of reasoning, in which premises were combined in certain ways to arrive at certain results, and at the same time, combining them in other ways would have led to utterly disastrous results, whether trivialization or just ridiculous results. And so, as I say, we're starting from the ground up and we're building models of actual reasoning rather than prescribing how to reason to people who come to us with just a list of premises or something like that.
Okay, so let's thank our speaker.
See you in 10 minutes then.
On the one hand, you have the structure, so that's necessarily